In a random experiment, the outcomes are, in practice, unpredictable. But generally speaking, we are more surprised at some outcomes and less surprised at others. For example, the winning numbers of a lottery are random, but we would be very surprised if they were the same as the numbers we chose. So, we'll introduce the following idea to quantify this level of surprise. The probability of an event is a number between 0 and 1 that quantifies our surprise at the occurrence of the event. If our event is A, we refer to the probability in one of two ways. We use this notation, or a little bit more distinguishing, we'll use this notation. An event with probability 0, because again our probability is a number between 0 and 1, this could still occur, but we'd be extremely surprised if it happened. So this is the type of thing where suppose you flip a coin and a bird swoops in and takes it before it lands. We can regard this outcome, bird swoops in and takes it before it lands, as a probability 0 event. Now, since an event is a set of some of the outcomes, an event could include none of the outcomes. So be a little careful here. Normal people would interpret some as being at least one, but not everything. But mathematicians are not normal people. Some means any number from 0 to everything. But if our event included none of the outcomes, well, that would just be the empty set. And since it has no outcomes to occur, the empty set can never occur. And so the probability of this event, the empty set, is going to be 0. Meanwhile, an event with probability 1 is an event that is certain to occur, barring the possibility of a probability 0 event occurring. So the event the coin lands heads or lands tails has probability 1, unless a bird swoops in. Now, since the sample space includes all possible outcomes of the random experiment, and an event occurs if one of its component outcomes is the result, then our sample space is an event that always occurs, and so we'll want the probability of the sample space to be 1. Now, in addition, we want our probabilities to satisfy one other feature. This is mainly because if they don't, they become impossible to work with and get any meaningful results. If we have two mutually exclusive events, A and B, then we want the probability of their union to be the sum of the probabilities. And so we'll put all of these together into a single definition. Remember, definitions are the whole of mathematics. All else is commentary. And so we'll define the following. Given a sample space S, a probability function assigns a value between 0 and 1 inclusive, could be 0, could be 1, to every possible event where the probability of the empty set is 0, the probability of the sample space is 1, and if we have two mutually exclusive events, the probability of their union is the sum of their probabilities. So from here, we can actually find a lot of probabilities. Let's consider complementary events A and A complement. Now, since complementary events are mutually exclusive, then our definition says the probability of the union is the sum of the probabilities. But since complementary events include all the possible outcomes, their union is the sample space. And we know the probability of the sample space is 1, and so we have. And for example, suppose the probability it will rain tomorrow is 0.3. Now you could say the complementary event is that it will be sunny, but you'd be wrong. The complementary event includes every other possibility. It could be sunny, it could snow, an F5 tornado could sweep through the region, and so on. So the complementary event to it will rain tomorrow is it will not rain tomorrow. So how can we find that? Well, the probability of an event and its complement have to add to 1, and so we already know the probability of the event, so we have the equation, these two things add to 1, And that allows us to solve for the probability of the complementary event. And so the probability it will not rain tomorrow is 0.7.